But right now, you're watching this video because first, God put at least one eyeball on your head, and second, because an operating system decided you could. It might be macOS if you're rich, Windows if you've given up on life, or Linux if you're part of the legendary 3% of gigachads out there. Either way, your CPU is probably running hundreds of programs at the same time. Chrome is somehow consuming an absurd amount of RAM, and yet your cursor still moves smoothly whenever you touch the mouse. That is not normal. It is a miracle performed thousands of times every second by one of the most underappreciated pieces of software ever written, the operating system.
The first operating system, GMNAAIO, was released in 1956 at General Motors because an engineer decided humanity had better things to do than manually feed punch cards into a giant IBM mainframe. It could run only one program at a time, had no memory protection, no users, no files, and somehow still managed to crash less often than Windows Millennium Edition. Nearly 70 years later, operating systems have evolved into incredibly sophisticated systems. By the end of this video, you'll understand how bootloaders, processes, scheduling, threads, system calls, virtual memory, interrupts, privilege rings, file systems, and many other components work together in perfect harmony. To do that, we're going to follow exactly what happens inside your computer from the moment you press the power button until the moment you rage quit and shut it down. Everything begins when you press the power button. Electricity flows through the motherboard, and the CPU wakes up in the most primitive state imaginable. At this moment, there are no files, no memory management systems, no applications, and no operating system. The processor simply starts executing instructions from a hard-coded address stored inside firmware. On modern computers, this firmware is known as UEFI, while older systems used BIOS. The firmware's purpose is simple. Initialize enough hardware to locate a storage device and then hand control over to a bootloader. The bootloader is a tiny program whose only job is to locate the operating system kernel on disk and load it into RAM. On Linux systems, this bootloader is usually Grub, the Grand Unified Bootloader. On macOS, it's iBoot. On Windows, it's Boot Manager. Regardless of the name, the responsibility is the same. Once the kernel is loaded into memory, the bootloader transfers control to it. At that moment, the CPU begins executing kernel code with complete hardware privileges. However, none of the things we associate with a computer actually exist yet. There are no files, no windows, no desktop, no applications, and no processes. The kernel has to create everything from scratch. Before it can do that safely, though, we need to understand one of the most important concepts in computing: privilege rings. Modern CPUs use privilege levels to separate trusted code from untrusted code. On x86 processors, there are technically 4 privilege rings, but only 2 really matter. Ring 0 is kernel mode, where the operating system runs. Code executing in Ring 0 can access hardware directly, modify memory, and perform virtually any operation. Ring 3 is user mode, where applications run. Programs in Ring 3 are heavily restricted and must request permission whenever they need access to hardware or protected resources. Right now, during startup, the kernel is running in Ring 0 with complete control over the machine. One bad pointer or mistake could potentially crash the entire system. That's one reason kernel development is notoriously difficult. However, this separation between kernel mode and user mode is also what keeps modern computers secure. Without it, every application would be able to read every other application's memory, interfere with running programs, and bring down the entire operating system. Because the CPU itself enforces these privilege boundaries, a buggy application can usually only crash itself instead of taking down the whole machine. Once privilege separation is established, the kernel begins constructing one of the greatest illusions in computer science: virtual memory. Here's the trick. When a program asks for memory, the addresses it receives are not real physical addresses. They are virtual addresses. These virtual addresses are translated into actual physical memory locations by a hardware component called the Memory Management Unit, or MMU. The MMU performs this translation using data structures known as page tables. Memory is divided into chunks called pages, usually 4 kilobytes in size. Every process receives its own page table, which means every application sees its own private version of memory. This isolation is incredibly important because it prevents applications from interfering with one another. Your web browser cannot directly read your password manager's memory, and your password manager cannot access your browser's memory. From the perspective of each application, it appears as though it owns its own private universe. To make this system efficient, the MMU maintains a small cache called the Translation Look-Aside Buffer, or TLB. Instead of repeatedly looking up address translations in page tables, the MMU stores recently used translations inside the TLB for quick access. This dramatically improves performance. Virtual memory also allows the operating system to pretend that more memory exists than is physically available. If a program tries to access a page that is not currently stored in RAM, a page fault occurs. When this happens, the MMU interrupts execution and notifies the kernel. The kernel then loads the required page from storage into memory, updates the page tables, and resumes the program. From the application's perspective, nothing unusual happened. The entire process is invisible. At this point, the operating system has established privilege separation and built the virtual memory system that keeps applications isolated from one another. The kernel now has a secure foundation on which to build everything else. With memory management finally in place, the next step is creating the file system, the layer that transforms a storage device full of numbered blocks into the files and folders we interact with every day. Now that virtual memory is up and running, the operating system can move on to the next major task, creating a file system. At the lowest level, your storage device is nothing more than a massive collection of numbered blocks. The hardware doesn't know what a file is. It doesn't know what a folder is. It only knows how to read and write blocks of data. The file system is the software layer that creates the illusion of organized files and directories on top of this raw storage. As the kernel starts up, it mounts the file system and begins making sense of the data stored on disk. Modern file systems store information using structures called inodes, short for index nodes. An inode isn't actually the file itself. Instead, it contains metadata about the file, including its size, ownership, permissions, timestamps, and most importantly, pointers to where the actual data blocks are stored on disk. What's interesting is that file names are not stored inside inodes. File names exist inside directories, which are themselves special files that map human-readable names to inode numbers. This design is why multiple file names can point to the same underlying file through hard links. Different operating systems use different file systems. Linux commonly uses ex4, Windows uses NTFS, and macOS uses APFS. While their internal implementations vary, they all solve the same problem, transforming raw storage blocks into a reliable and organized file structure. Modern file systems also include a feature called journaling. Before making major changes to disk, the file system records its intentions in a journal. If power suddenly disappears during a write operation, the journal allows the system to recover gracefully and avoid corruption. Instead of losing everything, the operating system can replay or roll back incomplete operations during the next boot. With memory and storage now functioning properly, the kernel moves on to another critical responsibility: loading device drivers. A device driver is specialized software that acts as a translator between the operating system and a specific piece of hardware. Every hardware component in your computer speaks its own language. Your graphics card, Wi-Fi adapter, keyboard, mouse, sound card, sound storage, and storage controller all require custom instructions. Drivers allow the kernel to communicate with these devices through a consistent interface. As the operating system boots, it scans the hardware connected to the machine and loads the appropriate drivers into memory. These drivers run in kernel mode, which means they have the same privileges as the operating system itself. This is both powerful and dangerous. Because drivers operate in ring 0, a bug in a single driver can potentially crash the entire system. Many famous system crashes, including the Windows blue screen of death, have often been traced back to faulty drivers rather than the operating system itself. Once the drivers are loaded, the kernel enables one of the most important mechanisms in computing: interrupts. Imagine if the operating system constantly had to ask every device whether something had happened. The CPU would waste nearly all of its time checking hardware status. Instead, modern computers use interrupts. An interrupt is essentially a signal sent by hardware whenever it needs immediate attention. For example, when you press a key on your keyboard, the keyboard sends an interrupt to the CPU. The processor immediately pauses whatever it was doing and jumps to a special interrupt handler inside the kernel. The handler processes the event and then allows the CPU to continue its previous work. The same thing happens when you move your mouse, receive data from the internet, complete a disk operation, or interact with almost any hardware device. Interrupts are what make computers responsive. Without them, every interaction would feel sluggish and delayed.